Okay. All right, so this is the first time that we're going to see an actual systematic approach to solving a PDE, or really it's going to be an initial boundary value problem where we have PDE initial conditions and boundary conditions. So this technique is called separation of variables. So we're going to have a PDE where we have derivatives with respect to two variables, so x for space and t for time. So separation of variables would involve separating that PDE in two variables into two ODEs, and ODEs each depend on one variable. And then we can use the solutions of those ODEs to obtain the solution of our PDE. Now, separation of variables is a wonderful technique for that. It lets you obtain a formula for the exact solution. Unfortunately, it can only be used in very limited circumstances. So it's essential that the PDE and boundary conditions are linear and linear and homogeneous. So there can't be any source terms. Although in the case where there is a source term, we can kind of adapt it to that. And that's something we'll see a few lessons down the road. And then it's preferable that the PDE boundary conditions have constant coefficients. I wouldn't say that is a must. Technically, separation of variables can still be applied if otherwise, but it's very difficult to in that case. So we're going to just use constant coefficients so you can see how the technique works in general. So, okay, still just 17 people. Dang it. Okay, so the idea is our solution is going to be u of xt. And it's going to be expressed as a linear combination of infinitely many functions un of xt, where each one of these is a solution of a PDE, and it also satisfies the boundary conditions. We just need to find the right linear combination of them using these coefficients an, so that the solution also satisfies the initial condition. So we're really going to deal with the PDE and boundary conditions first, and then we'll account for the initial condition at the very end of a process. Also, these solutions to the PDE, we're going to break that down further, but we're going to assume that it's a product of a function of x only and a function of t only. And these will come from solving the two ODEs that we separate the PDE into. All right, so now how do we achieve that separation? So to make things more concrete, here's a problem we're going to tackle. So we have a heat equation on the interval 0 to 1. And then here we have the initial condition. When you plug in t equals 0, you get 5x, where 5x we assume is some given function. And then we have our homogeneous boundary conditions that the solution is equal to 0 at the boundary points x equals 0 and x equals 1. So what we do is we assume that un of xt is a solution of a PDE and that it has this form. So then we substitute this into the PDE. So when we differentiate this with respect to time, xn of x is treated like a constant, and we just take a derivative of tn. So we have a tn prime there. Similarly, we take a second derivative with respect to x. We only differentiate, oh, typo, that should be xn double prime. Okay. And then tn is just left alone. So now we have this situation. So now we go ahead and divide both sides by xn and tn. and we end up with this. Now, we could really put the alpha squared in either fraction, but for convenience, we just put it in here. Okay, now how the separation is achieved is by taking into account the fact that this left side of the equation is a function of only t. Right side is a function of only x, but they have to be equal, regardless of what x and t are. The only way that these two functions of two different independent variables can possibly be equal, regardless of x and t, is for both of these fractions to equal a constant. So, so we assume that both of these are equal to some constant k. So then I can say that so xn double prime over xn is equal to k, and that leads me to this ODE from the right side. And then similarly, I have this ODE from the left side. So that is how I've separated a PDE in two variables into two ODEs, each of which depends on one of the two variables. So now I can go ahead and solve these two ODEs independently of one another and obtain a solution of the PDE. And then the boundary conditions will affect this one, because this is the only ODE that is where solution depends on x. So only it has to satisfy the boundary conditions. And these are boundary conditions from the original problem, but applied to xn. So at the two boundary points, it must be 0. Now, right now, we don't know anything about k. It's just some constant. But we need to check for which values of k can there possibly be a solution that satisfies the boundary conditions. Now, the boundary conditions are homogeneous, so the solution is equal to 0 on the boundary. Now, that might mean that xn must be 0 everywhere. Well, we don't want that. We need solutions that are non-trivial, that are non-zero. So what I'm going to do is look at different possibilities for this constant k and see what conditions it has to satisfy to make sure that we're going to get a non-trivial solution. So first I assume k is 0 in this ODE. So now it reduces to xn double prime is 0. Well, the solution of a ODE like this has to be a linear function of x. So it's something that has this form for a and b inner constants. So now what I can do is I can apply the boundary conditions. So I can set x equals 0 and x equals 1. And so when I plug in x equals 0, I get this. And I plug in x equal 1, I get this. So the only way that both of these can be satisfied, bn equals 0 gets plugged in here, and I get an also equals 0. So we end up with a trivial solution. So in other words, k equals 0 is useless. It will not give us any contribution to the solution of the overall problem, so we discard it. Now, what about k positive? So in that case, this is a solution of the ODE, where we have these exponentials with exponents that are negatives of one another. So now what we could do is apply the boundary conditions again. So we plug in x equals 0, so the exponentials become 1, and we get this equation. And then we have this equation, we plug in x equal 1. Now, if we were to write this system of equations in matrix vector form, it turns out that this matrix, the matrix of a system, would have a non-zero determinant. When that happens, because the right-hand side values are 0, the only solution, so this is from linear algebra, the only possible solution is a trivial solution. So positive k is also not going to help us. So the only thing left is negative k. So what happens in that case? So this is a general solution now. So the fact that we get a general solution like from this case and this case, that actually comes from what you learned in your first course in ordinary differential equations. When you're solving an ODE like this one, what's the standard approach? Well, you take the characteristic equation, which in this case would be r squared minus k is equal to 0, and solve it for r to get your two roots. And then depending on what the roots are, if they are real, distinct, or real and repeated, or complex, that tells you what form a solution has. When k is positive, your characteristic equation has two distinct real roots. That leads to this kind of solution here. When k is negative, you have r squared plus k is equal to 0, or plus a positive constant is 0, and you have complex roots, and that leads to this form of a solution right here. So all that falls back on what you would have learned in your first differential equations class. Now, k is assumed to be negative. So then we're taking a square root of a positive number. So just for convenience, of notation, I'm going to say k is equal to minus lambda squared because this is definitely a negative number. So now the solution has this form. So we want to see if this can satisfy the boundary conditions, and it better because it's our only option left. Now, before I get to that, if k is equal to minus lambda squared, this is the ODE that we have in time. So we have to solve this also. So here we're using this equation is a linear and also separable ODE. Again, something you would have learned from your intro course on ordinary differential equations. This is a solution in that case, and where Cn is some arbitrary constant. But remember, Tn of t is going to be multiplied by xn of x, which also has arbitrary constants in them. So we don't need that many arbitrary constants. So we'll just set Cn equal to 1. So now this is a solution to the PDE for any positive value of lambda. So our solution to our original problem, u of xt, is going to be a linear combination of these. As long as we can make sure that that this part can satisfy the boundary conditions. So we've solved the PDE up to this point, or we have a parameterized family of solutions of a PDE that we can work with. Now we check the boundary conditions. Once we deal with that, we'll move on to the initial conditions. So we go ahead and set x equals 0 and x equal 1 in here. So this is what we get from x equals 0. This is what we get from x equal 1. Well, the exponential could never be 0, so bn is 0. So in other words, for this case, if these boundary conditions, there's no cosine term. So now this equation, we drop the cosine term, and this is what we have. Now, the exponential can't be 0. We need a non-trivial solution, so an should not be 0 either. Therefore, sine of lambda must be 0. Now, when is sine equal to 0? This is one of these things that you learn about in trigonometry, and it's a good thing to just keep in mind because it keeps coming up in all kinds of problems. When is sine equal to 0? When the argument is an integer multiple of pi. Just like when is cosine equal to 0? Well, that's when you have an odd integer multiple of pi over 2. So these are just one of those good to know, a couple of those good to know things that come up in many different situations. All right, so in this case, lambda must be an integer multiple of pi. So now we have a solution of this form. Now, why did I specify that n must be a positive integer? Because this will hold for any integer multiple of pi. Why does it have to be positive? Well, here's why. If n is 0, we get sine 0. So the whole thing would be 0, it'd be a trivial solution. What about negative integers? Well, we could let n be negative, but it turns out we gain nothing from it. And the reason why is we take sine of minus n pi x. Sine is an odd function, so that's the same as minus sine n pi x. In other words, we would get, if we let n be any non-zero integer, we'd have solutions here that would be negatives of one another. In other words, they don't make any contribution. Why? Because they're not linearly independent of one another. So by allowing negative integers, we would get new solutions that are linearly dependent on the ones we already have. So to get a minimal set of solutions that are actually useful to us, we just restrict n to being positive. So that way, when we take a linear combination of these solutions, the coefficients will be unique. So our solution to our original initial boundary value problem is now known to have this form, where we have our elementary solutions of a PDE times some unknown constants, add them all up. So this linear combination of these solutions of a PDE that satisfy the boundary conditions will also satisfy the initial condition when we plug in t equals 0. So when we plug in t equals 0, the exponential goes away, and u of x0 must be equal to phi of x by that initial condition. So our coefficients an now have to satisfy this. So how are we going to get coefficients to ensure that this is satisfied? We use this very nice property of these functions sine n pi x. So if I evaluate this integral, sine of n pi x times m pi x, and we assume that m is not equal to n. And remember, m and n are both positive, so this will be non-zero, and this will be non-zero. So I go ahead and carry out the integration, and so I'm not dividing by 0. But what will happen is I'll plug in x equal 1 and x equals 0. When I plug in x equal 1, I have sine of an integer multiple of pi. And plug in x equals 0, I'll get 0 because sine of 0 is 0. So the point is the whole integral evaluates to 0. And that's going to be very helpful to us. What if m is equal to n? Then I have integral of sine squared n pi x. And what I could do here is use a half angle identity. So yep, you got to dust off your knowledge of trig identities. And we can write it this way. Now it's in a form that we can integrate. So we go ahead and carry out the integration. This part, the x, is the only part that makes a contribution to the value of the integral. So we end up with 1/2. So what this means is these functions, sine n pi x, they are an orthogonal set of functions. Oh, typo. Orthogonal. Okay. Whoops. Okay. Now, in calculus, you would have learned about how if you have two ordinary vectors, like vectors in R2 or R3, you take their dot product, and if they're equal to 0, if a dot product is equal to 0, then the vectors are orthogonal. This is very similar with vectors that are functions, because you can define a vector space consisting of functions. This multiplying the functions together and taking their integral over a certain interval, that defines an inner product. If the inner product is 0, the functions are orthogonal. So that's what we have going on here, that we have this orthogonal set of functions, and that's going to be very useful to us in getting these coefficients an that we need. So here's what I do. I go back to this equation here. And I multiply both sides by sine m pi x. So that's what I have here. And then I integrate both sides from 0 to 1, the domain of my PDE. Now the sum and the constant I can pull out. So now I have all these integrals. And m is some fixed positive integer, and n varies over all the positive integers. Now this integral, based on what I showed you a little while ago, is going to be 0 because of your orthogonality of sine m pi x, unless m and n are equal. So if that happens, then the integral is 1/2, and we have a m. So now all I have to do is multiply both sides by 2, and now I have a formula for my coefficients. So here's a solution of the original initial boundary value problem. And here are the coefficients, 2 times the integral from 0 to 1 of this. And this also is like an inner product of your initial data phi with sine n pi x. Now, I want to emphasize the reason that the constant is 2 stems from the fact that the interval is the domain of our PDE is 0 to 1. In general, the scaling factor we have here is 2 over L, where L is the length of whatever interval you have. And that is a result of what we have in this integral here. All right, so just be aware of that. It's not always 2. It's that's because of a particular spatial domain we have. Now this series here, we'll learn more about this down the road, is a Fourier sine series. So we're expressing phi of x as a linear combination of these functions sine n pi x. Okay. Now, if phi is continuous and the values at the endpoints match, okay, actually I need to be more specific here. As opposed to Fourier series involving sines and cosines. So if it satisfies the boundary conditions, so phi is continuous on 0, 1, and is 0 at the endpoints 0 and 1. Then for every x in this interval, this series will converge to phi of x. Otherwise, there's going to be some discrepancy. And then how do we get to coefficients? We take advantage of your orthogonality of these functions, sine n pi x. So this formula would give us the coefficients of that Fourier sine series. Okay. All right. Now, if we look at the formula for our solution that we have here, what happens is, oh wait, typo, that x should not be there, it should just be n pi. Okay. What happens as t increases? Well, it turns out that the here we have a decaying exponential. So this factor is going to go to 0 rapidly as t increases, especially for larger n. So also as we look at the terms of a series, n equals 1, 2, 3, and so on, these terms are going to get pretty small as n gets larger. So in fact, what you could do to get a decent approximation of a solution is just look at the term for n equals 1. So this term right here, the first term of that Fourier sine series, is a reasonable approximation of a solution. And in fact, especially so as t gets larger. So this could be helpful in understanding in a qualitative sense how the solution behaves as a function of x and t. In general, the smoother phi of x is, the more rapidly these coefficients an go to 0. So in that case, you may be able to get away with just using a few terms of a series to get a decent approximation of u of xt. So this is how a process of separation of variables works. Now what? Okay, I want to point out, this is important for you to use later. The reason why the solution turned out to be a linear combination of sines because of the Dirichlet boundary conditions, meaning the solution U is equal to 0 on the boundary. You have Neumann boundary conditions, where you have du dx on the boundary. In that case, the solution is a linear combination of cosines. So this is one of those good to know things, because you'll be solving lots of problems using separation of variables or certain variations throughout the semester. That when you have these kind of, so the boundary conditions dictate the form of your solution. Is it a linear combination of sines and cosines? And if you have certain different combinations of boundary conditions, like maybe you have Dirichlet on one end and Neumann on the other end, then that can affect whether you get sines or cosines or possibly both. That's something that can happen. So, so keep it in mind that when you look at one of these problems that I might assign, like, okay, here's your initial condition, here's your boundary conditions, and you see, oh, U is 0 on the boundary at both boundary points, then bam, it's, you know, your solution is a linear combination of sines. Okay. So sure enough, I've come to the end already. I'll find a better way to fill the time. But this also leaves plenty of time for any homework questions. So, so does anyone have questions either about what I did presented just now, or about homework from lessons 1 through 4?
I do have one question.
Okay.
Lesson 4, it's the last homework question. I believe it's number 4.
Okay, I'm gonna get that pulled up here. Okay. Whoops, scroll down way too far. Dang it. Okay, so lesson 4, number 4.
Yes, deriving the equation. I guess I'm just not quite sure where to start, maybe.
Okay, I'll get the screen shared for that. Okay. All right. All right, so when you have change of mass inside this segment, and one of as far as how you handle, so of course the first two parts of it, change of mass inside x plus delta x, and then change to diffusion, that's going to be handled exactly the same way as in the derivation of the heat equation shown here, which is essentially what I covered in the notes last time. So
right,
have your conservation. Okay, so you have that part and that part not changing from before. So what happens now is what you're going to add to that is, okay, So then you're gonna so the other term that you'll throw in here is okay. Change of material being carried across the boundaries. So you're gonna have so that's going to lead you to some terms involving just u evaluated at x and x plus delta x. And okay, so then we have okay, moving with velocity v. So that's why v is going to be a scaling factor in this case. Okay, and so what's going to happen is okay. Let me see if I can get myself typing into this. Okay. Okay. So for a term moving through the left boundary, okay, so we need to move this real quick. So you want to account for left boundary and right boundary. So and keep in mind that velocity is going to be directional, and it's material being carried across the boundary. So something that's going to be coming into the segment is going to be added. Something that's going to be leaving the segment is going to be subtracted. So for the left boundary, you're going to have because that's going into the segment, that is going to be added. So you'd have a term v times u of xt. And then for right boundary, that is going to have to be subtracted x plus delta x times t because it's leaving the segment. So just as the terms we dealt with last time, how I dealt with this, and I used a somewhat different approach than what was shown here in the book, I think. But you can use the same idea. Just as these terms led to uxx, then the terms I just described can lead to an inclusion of ux by applying a fundamental theorem of calculus like I showed you on Monday. Oh, actually, I do need to include this, the cross-section area. Just to make sure everything works out like it's supposed to. Okay. Does that answer?
Yeah, that helps. Thank you.
All right. Okay. Any other? Oh. someone's already left. Actually, when I take a look at what I have queued up for Monday, okay, so that's just going to be lesson 6. These are notes that I'll adapt, but just what I can see here, there will certainly be time for homework questions on Monday also, if you don't have any now. But so last chance, you all. I guess everybody's like, yeah, I want to get out of here. Okay, so that'll be all for today, and be sure to have to spend time on the homework between now and Monday. Well, Monday's when it's due, and so you can ask any questions then. So let's get the recording stopped.